And so, hello and welcome everybody to today for what is now amazingly our 38th Inspiration Exchange session. And I'm delighted to be hosting the session. And my name is Fergus Imrie. Today's session is going to be covering advanced topics in diffusion modeling. And I'm really excited for today's session. So to start with, we're going to kick off with two talks from members of our group. First will be on time series diffusion by Nico, and then Yanming will present on soft mixture diffusion and on error propagation in diffusion models. I'm then delighted to welcome two guests from industry, Dr. Sander Dieleman and Dr. Max Ilse, who I will introduce more formally later on in the session, who'll be joining us for a roundtable panel discussion and for the Q&A portion of today's session. But in the meantime, we are going to start with the talks for members of our groups. If anybody has any questions at any point for either of our two speakers or our two panelists, please ask them in the Inspiration Exchange channel on Slack. And if you're not a member of our Slack channel, we'll post a link to this in the chat now, so you can join and ask questions there for any of our speakers or panelists today. So without any further ado, we're going to start with Nico, who will be speaking on time series diffusion.
So today I'm going to talk about our project on time series diffusion in the frequency domain. And this work is going to appear at the upcoming ICML conference. So let's first start with some motivation and why the problem of generative modeling for time series is important. So first of all, in generative modeling, what we are interested in is approximating a complex data distribution P data, from which we observe some samples. And usually what we do is that we train a model, which can then be used to obtain new samples. And having said that, we are going to focus in this work on time series, which is an important modality. And it appears in critical domains, such as finance or healthcare. So for example, in electronic health records. Researching regenerative modeling for this modality is important for several reasons. First, it's relatively underexplored compared to static modalities, such as images or text. And second, it has many important real-world applications. So in the healthcare domain, for example, there are many regulations around the sharing of data. And if you have a generative model, then you can use it to reconcile privacy with the development of ML models. And generative modeling can also be used in data augmentation, where you can use the generative model to obtain new samples to help in downstream tasks. So to summarize, today we're going to focus on obtaining performant generative models for time series using insights from the frequency domain. So there are different methods which can be used for generative modeling of time series. One can use, for example, GANs or normalizing flows. And in this work, we are going to focus on diffusion models because they have been highly successful in static modalities, such as images. And they have been shown to be easier to train than GANs and able to produce high-quality samples. So I will first start with some basics about diffusion. So I'm going to focus on the general continuous time diffusion modeling framework, for which the formalism builds on stochastic differential equations, or SDEs. And at a very high level, it works like that. So you have a distribution P data, and this is a distribution that you want to approximate. Then you're going to transport this distribution to a generic distribution P0 via what is called a forward process. And this usually entails adding, for example, some Gaussian noise to the observed samples. You can then reverse this forward process and obtain what is called a backward process. And usually P0 is chosen to be a simple distribution, such as an isotropic Gaussian, from which it's very easy to draw samples. Let's look more closely at the forward and the backward process. So in the forward process, we operate on a given representation, denoted here as X. So in the context of time series, you can think of X as the vectorized time series. And then you have a drift term via this function F, and a diffusion coefficient G, which modulates standard Brownian motion So this is where the stochasticity comes from. You can then reverse this forward process and obtain what is called a backward process. Again, you have a drift function B, but this function depends on the score function written here. And in practice, we can estimate the score function using what is called denoising score matching with the forward process. And again, we have a standard Brownian motion, which gives the stochasticity. So if I have an approximation of B, then I can use the backward process to sample from an approximation of P data. So in the previous slide, we have written a general recipe to perform diffusion, and the diffusion process intuitively adds some noise to the representation. And in the context of time series, this would be like adding noise to the different components of the time series. But so far, we have not really exploited the characteristics of time series. And here comes the key idea of our work. So we want to use a different representation of time series instead of operating directly in the time domain. And we do this by drawing inspiration from Fourier analysis, which has many applications in signal processing, and which provides a convenient way to work with time series. So for example, it has been previously applied to compression or filtering in signal processing. And in this work, we deal with discrete time series, and we're going to use the discrete Fourier transform to obtain frequency representations. And the natural question here is, what happens to the diffusion process that we have just defined on the previous slide? So in proposition 3.3, we showed that this diffusion process is mapped to another diffusion process, but this time in the frequency domain. And both the forward and the backward processes are mapped to corresponding forward and backward processes in the frequency domain. And this is what we're going to look at in the next slide. And what is great with the property of the previous slide is that it provides us with a recipe to perform diffusion in the frequency domain, starting from a diffusion process in the time domain. So we describe here the forward and the backward processes. As you can see here, now we operate on frequency representations with the tilde. We have a drift function f tilde, which depends on the original f. And the stochasticity comes now from what we call a mirror Brownian motion. So this is detailed in lemma 3.1 in our paper, but very simply that describes the effect of applying a DFT to a standard Brownian motion, sorry. And this entails in particular enforcing some symmetries between the components. Again, you can reverse this forward process and obtain a backward process, which is described via this SDE. And taken together, those two components give us a simple recipe to perform diffusion in the frequency domain. So we're going to first obtain frequency representations of the original time series. And then we're going to use the forward process to have an estimate of the drift B tilde using denoising score matching. Then we can use this backward process to obtain frequency representations. And finally, we can obtain time series using the inverse DFT. We now turn to the experiments. And the first question is, of course, does diffusing in the frequency domain lead to better models than diffusing in the time domain? And to answer this question, we consider a wide range of datasets spanning different domains, such as healthcare, finance, or engineering. For each of those datasets, we're going to train one diffusion model in the frequency domain and one diffusion model in the time domain. And we are going to compare those models using sliced Wasserstein distances with respect to the original empirical distribution, both in the frequency and the time domain. And as we show here in this column, in bolded, the frequency diffusion models outperform the time diffusion models across the different data sets. So this shows that the frequency diffusion models better capture the training distributions compared to the time diffusion model. It's then natural to ask why this happens in practice. In our paper, we provide more intuition on this phenomenon by performing first a signal energy analysis. So on this first plot, you can see the energy density in the time domain for the different datasets. And on this plot, you can see the spectral density. So this is now in the frequency domain for the different datasets. And as you can see here, there's a huge asymmetry between those two domains, because in the time domain, the energy density is kind of uniform in all of the data sets, whereas in the frequency domain, you can see that there's a clear localization here in the low frequency region. And intuitively, the frequency score model is going to see those representations of time series where most of the relevant information is concentrated in only a few components. So now we make this intuition of localization more quantitative by computing a localization metric. So in this plot, you can see the delocalization, which is the opposite of the localization, as again, this confirms our intuition that the data sets are more localized in the frequency domain than in the time domain. And we have additional experiments in our paper which confirm the importance of localization, where we intervene on data sets by artificially manipulating the localization, and we show the impact on the performance of the models. So to conclude, we focused in this work on the important task of adjective modeling for time series using diffusion models. We formalized frequency diffusion starting from time diffusion using the generous continuous time diffusion modeling framework. And we showed that operating in the frequency domain is better across the data sets that we consider. And we also give some intuition for why this happens in practice via the notion of localization. So we focused in this work on the representation part of the time series, but of course, one can also improve the diffusion methodology, and this would naturally lead to better diffusion models. And this aspect is going to be covered in the next presentation by Yang Min. So here, there's a link to the paper if you want to see the details. And feel free to ask any question. Thank you very much.
So I will first introduce a paper of soft mixture denoising. This paper is actually a study of the approximation capability of diffusion models. We aim to study its problem and improve the models. And with our method, we can make it diffusion models faster. So conceptually speaking, diffusion models is like sampling from to iterative sample from noise. And this process is called backward process, and it's very long. It may take like 1,000 steps. So because the backward process is very long, so it takes a long time. So its sampling efficiency is very low. So many works in practice will use a very small t to get a good efficiency, but in that sense, you will have very bad generation quality. So here is like a very synthetic experiments we done with diffusion models. This is our method, and this is the baseline DDPM. You can see like even for very simple mixture data, DDPM might fail. But there are also other better backward solvers like DDBIM and DPM, all these methods. But they are aimed at deterministic sampling and achieving better numerical stability. So they can't avoid. We think they can't inherently solve the problem. For example, why small t will lead better generation quality. As I say, the core of diffusion is the backward process, which is to match the forward process. And every step of the backward process is to approximate a reverse probability. And this learnable model is assumed to be Gaussian. So our first finding is like we find for certain data distributions, actually, which will be very simple, like Gaussian mixture. The reverse probability is also a Gaussian mixture. And so this is a result implying that the current Gaussian assumption might not be qualified. But somebody will ask like why even though you have this proposition, but why diffusion model already perform very well? So another insight of this finding is like if t this backward process t this iteration number t become very big, so this wk will convert to a one hot vector, which means this will become a Gaussian. But for few backward iterations, this will the non-Gaussian phenomena will be very obvious. There are things. There is just intuition. So somebody will say like maybe this is not a big problem. So we did a very deep theoretical analysis on how the impacts of this non-Gaussianity will affect the model performances. So we first defined two errors, two metrics. One is the local denoising errors, which means which represents the performances of each denoising model. And the other is like approximation errors, which means if we regard this backward process as a whole, how well it will perform or how bad it will perform. So our theorems find like both errors are unbounded for a very simple data distribution, for example, Gaussian mixture, and especially like this WT, which means local denoising error, is uniformly unbounded because there is a it has subscript T, which means which time step. So we find like for there is a distribution, which means like for every time step T, this metric is unbounded. So and there is an inside like unbounded error estimation errors, which might be useful for current theorems because they all assume like the error estimation errors is bounded. So how to solve this problem is because of our previous conclusion is also very simple. You just parameterize the backward process as a Gaussian mixture. But there might be some difficulties if you do so. For example, the Gaussian mixture models is hard to optimize. And the other point is like there is an argument K, which is the number of the components, which you can determine it before for unknown data distribution. So we introduce a continuous relaxation of the Gaussian mixture to solve this problem, which is very simple. We just relax this discrete variable into continuous time, continuous lantern variable. So this is like a full probability expansion of this term, and you just factorize this in this way, and this term is just a Gaussian because you already know which component it is. So for each component is a Gaussian, and this is a distribution of the mixture. You can imagine it like a normalizing flow, which maps a very simple distribution to a harder one. Because this is a new denoising paradigm, so we need to have a new loss function for it. Is the upper bound of the log likelihood, which is shapes like this. Even though our model seems like more complex, but actually the training and sampling efficiency and procedure are almost as simple as ordinary diffusion models. The blue areas highlighted here show the difference. You can see the only difference here is like we have an additional lantern variable sampling, and with these lantern variables, we will select a new parameter set for the Gaussian, and you just do the gradient descent. And sampling is similar. You just additionally sample the lantern variable, which means mixture component. So we did experiments to verify the effectiveness of our model, because obviously our method will be very useful in the case of a few backward iterations. So we apply our method to lantern diffusion, a stable diffusion, which is very advanced diffusion models. In the case of 100 backward iterations, you can see like in terms of both image quality and FID scores, we are much better. Especially like we only use 10/10 of the backward iterations, but achieve the similar FIT scores. You can see here 5.2 and 6.8. So that's the first paper. The second one is about a study of the structural risk of diffusion models. We all know like diffusion models is a long chain. So this type of structure in sequential models have a very famous and classical problem called error propagation. You just imagine, for example, here is 3 components, because they are chain structure. So the prediction error of this module might have bad impacts on the next module. And if the chain is very long, so the error will accumulate it. So if you imagine this term is like, for example, this term module term is like the prediction error of every module of each module and of some module, and this is the cumulative error in this module. So the key point is to determine this mu-t. So if this mu-t is bigger, is smaller than one, then we shouldn't worry about this, because seems like the error will decrease. But if it's greater than one, you have big problem because the error will accumulate it. But this is just intuition. We haven't we can't say for sure. So we did a comprehensive study on this problem. So we first defined what is the errors of each module, which means each denoising step, and we also defined what is the cumulative error, which means, for example, I just regarded these two module as a whole. What's the error of this whole module? These two modules. And with this definition, we can find a propagation equation, and you will find that the mu-t here is actually 1. So the error propagation happens to diffusion models. But this theory is with some mild conditions. So we are interested in verifying this our theory in practice. But actually, diffusion models is hard to estimate the density. So we propose we use another measure, MMD, instead of the KL divergence to measure the errors. Actually, the new measures is tightly bounded the original one, which only 1/4 of the 1/4 difference. And here is the experiment result. The x-axis is denoising steps. You can see like the errors just grows, exponentially grows, which is even beyond the linear complexity here. So these experiments strongly say like error propagation happens. So how to solve this problem is also very simple. We just because we already have an upper bound which is computationally efficient of the cumulative errors, we just impose this as a regularization. And after applying this, we can see like the error propagation phenomenon just disappear. And at the meantime, we also observe the performance increase, which means we get a lower FID scores. And we also did a balance. So this is like the bootstrapping steps is to make this term more computational efficient. So we started like not increasing too much time, but our FID scores dramatically decrease. So that's all. Thank you.
Now it is my pleasure to move to the panel discussion and to introduce our two guests for today. Our first guest is Dr. Sander Dieleman, who's a research scientist at Google DeepMind, and in the past has worked on projects including AlphaGo and WaveNet, and his current research interests are in generative modeling and representation learning, with a focus on audio signals and music. Also delighted to welcome Dr. Max Ilse, who is a senior researcher at Microsoft Research in the Health Intelligence Group in Amsterdam, working on medical image analysis as part of Project Inner Eye. Thank you, Sander, and thank you, Max, for joining us today. I wanted to just kick off the discussion maybe by allowing you both just to say a few more words to introduce yourself, kind of what you're working on and some of the things you've worked on in the diffusion model space thus far, before maybe getting into some more specific questions. So I don't know who, maybe Sander, if you could kick us off with this.
Sure. Yeah. So the bio you read is slightly outdated in that I have been working on music recently with the Lyria model that we put out, but I've also been working quite a lot on the other perceptual modalities, images and video. So we recently put out our latest image model, Imagine3, which I had a hand in, and then also our video model, Vio, which was demoed at Google I/O last month. So I'm kind of across all the modalities. I also recently, well, about 2 years ago, did some work on trying to apply diffusion for language modeling. So I've kind of covered all the bases, I suppose.
Oh, no, awesome. Thank you for the correction there. I appreciate it. Max, I don't know if you wanna go next.
Sure. So for me, the opposite, mainly medical imaging. And what we look into a lot is like synthetic data and applications of synthetic data, and a few things that we come across now is like really the problem of bias in the data. Like diffusion models pick up the same bias your synthetic data generated by these diffusion models as bias as well. And from my point of view, I feel like there are two interesting directions I see emerging. One is kind of the whole research around compositionality and also compositional generalization, where you can kind of chain diffusion models, conditional diffusion models, to create outputs it might have not seen in the training data in terms of composition. And the other thing is kind of just more controlled generation, right? Like a lot of like ideas, especially in the image space, like using masks doing the generative process. Like not sure, like if you've seen diff edit and all these different edit methods that are floating around. One problem that we are facing there in the medical imaging community is that getting masks is really laborious, right? Like you need a doctor most of the time to really give you a high quality mask. There are now methods that say like, oh, the diffusion model can actually also give you the mask in addition to generate images for you. But from our experience, if your diffusion model is biased, then your mask that comes from the diffusion model is also biased. So yeah, that is what I have on the top of my mind most days.
Awesome. Thank you both for that. I was going to start somewhere very different, but Sander, something you already said kind of piqued my interest there about, especially with your quite unique experience of working across modalities. How transferable, I guess, do you feel, not the models themselves, but kind of the insights about what works in one modality versus another, do you see in diffusion models, or are there quite different insights and modeling approaches really needed to get the most out of these models for different modalities?
I think across the perceptual modalities, there's a lot of transfer, because human perception of visual perception and sound perception kind of work in similar ways, have similar characteristics in terms of the relative importance of different frequency bands in the signal. And this is something that diffusion models really capitalize on. And so there's been quite a bit of transfer. The odd one out is language modeling, out of the ones that I've worked on, where a lot of these ideas don't apply. Like you can't really decompose. Well, you could try to decompose language data into frequencies, but what does that mean, right? It's like it's much harder to kind of have intuition about that. And so I think a lot of the work that's being done is evaluated on images, and so could reasonably be expected to generalize to other perceptual modalities and maybe more specific subsets of the image modality, like, for example, medical images. But if you go sort of too far out of that comfort zone, a lot of stuff breaks down.
Do you think that's kind of an inherent limitation of diffusion models themselves, or is this something that maybe will get fixed over the next few years?
So I think it's the reason they kind of came in and took over all modalities except text, I think, is primarily because diffusion models have this implicit benefit of being able to focus on the parts of the signals that matter perceptually. And this is something that was kind of discovered by accident. I don't think people realized this when they started doing diffusion on images. They just tried it and said, oh, actually, this works really well, so we should lean into this. It's only later that we figured out, oh, actually, it's because the loss function that you optimize when you train a diffusion model inherently, sort of out of the box, puts more emphasis on the parts of the signal that are perceptually relevant, which is the lower frequency content in a nutshell. Sorry, where was I going with this? So I think that that's one aspect where that's the reason why we have diffusion models now and why they're so popular. That does not mean that they can't work for other modalities, but you might not have that inherent advantage there, right? So you might have to work a little harder to see the benefits. But of course, there could be other advantages. Like one interesting sort of idea that's arising is that maybe in the language domain, diffusion is a better substrate for reasoning than autoregression, because you can go back and fix things that you've decided before, whereas autoregression cannot do that, right? Autoregression, you kind of commit to a token, and then that token is fixed. Whereas with diffusion, you can kind of reason over all the tokens simultaneously.
Oh, no, thank you. I think that's super interesting. Max, where do you see really then, do you think, I guess with Dieleman, that kind of answers the kind of a question about like maybe some of the general areas being perception being a very important area. In medical imaging, do you kind of see this the same, that diffusion models there are getting ground because they are just a better generative model than maybe what's come before for these types of images? Or is there something else there that is making kind of diffusion models very popular or perform better or more useful? And are there any particular applications you're really excited about within the medical space?
Yeah, coming back to what I initially said, I feel like there are more papers pointing towards the direction that diffusion models are the first generative models that can really do this composition. And I feel like this is really, really important. I think I just today saw a really good paper of Okawa et al., where they really like went through the steps of having a synthetic data set and then really playing around with that and showing it really can compose unseen combinations. And I feel like this is, for us at least, really the key aspect, because I had a lot of fun with like VAEs and normalizing flows to try to make this work. And you always feel like, oh, you're almost there, but the one corner of your data distribution will always be empty if it's not captured by the training data. I wish I had a paper.
Awesome. No, thank you. Yeah, I just saw that question in the chat. So I guess on this note about the models, obviously diffusion models are very popular now. We're seeing like a lot of excitement in many areas, including in science, kind of beyond. I guess you could see it as a visual problem with like AlphaFold 3 for protein structure prediction and beyond now. But I guess we've seen in the past other models kind of have a lot of dominance in the image generation space. So I guess the maybe slightly provocative question is, do you both think diffusion models are kind of here to stay, or is there perhaps a kind of a new model on the horizon in the next year or two that captures something missing from diffusion-based approaches? Not sure, Max or Sander, which one of you wants to maybe take this one first?
Sure, I have some thoughts about that. So I think we have this interesting situation right now where diffusion has come in and kind of taken over pretty much all the modalities except language, right? Language is still firmly autoregressive. I actually wrote a blog post about this a while ago, about why this might be. And I think it's a very interesting situation because I think it's an unstable equilibrium. I feel like in the long run in machine learning, the stuff that survives is very simple, very straightforward to understand. That's what, of all the stuff that was invented 10 years ago, that's the stuff we still use. And so my feeling is that given that the future seems to be kind of moving towards multimodal models that understand all the modalities jointly, that you can speak to with language, but they also understand images, they understand video, they understand sound, and they are able to produce those modalities as well. I think in that setting, the question arises, how long are we going to tolerate this, this balancing of two different modeling paradigms that we currently have? And I think personally that eventually we'll grow tired of that, and it's going to collapse back either we just go back to autoregression for everything, because we know that also works, right? You can generate images autoregressively, and that works reasonably well. Or maybe we figure out how diffusion for language should work at scale, and then maybe we can look into building diffusion models for all modalities. I think a big question there will be, how do you kind of balance the different modalities? How do you create a corruption process with information in an even way? That's something that I think there hasn't been a lot of research into that. But yeah, that's sort of my general feeling about this. It's also possible, of course, that a new modeling paradigm enters the fray that takes out both of them at once. I do think, though, that it will be iterative. I think the key to scalable generative modeling is iterative refinement, which is something that you find both in autoregression and in diffusion. And I think that is definitely here to stay.
Yeah, thanks. Yeah, I think that's super interesting. I really enjoyed you picking up on that kind of iterative refinement point. I fully agree. I know a lot of people in the language modeling space are talking about that, and a lot of the, I guess, like very almost like manufacture, like all of these prompts. It's almost trying to prompt the model to somewhat at least do that. At least is the heuristic that I think people are thinking. So I think there could be some exciting times in model development in the next couple of years of how can we maybe incorporate those ideas from that are popular in diffusion beyond. Max, did you want to take that question as well?
I would just want to add like a very minor thing to what Sander already said, because I fully agree. I think what we have seen the same evolution in like just image modeling, right? Like there are enough papers that show you could have a ResNet or like a CNN-based model that could totally do as well as a vision transformer, but I feel like there's like something inherent in our field to move towards the same model. So I totally agree with Sander. So right, like we all know use vision transformers for most things, and I'm not sure what the reasons are, but I guess once you get used to a certain paradigm, then it's easy to use everywhere if it works.
Could this vary by scale? So I guess scale in this sense meaning kind of like data scale, because a lot of these models we're talking about is where we've got kind of abundance, a real abundance of data, and there we're able to almost take away a lot of the extra structural constraints of models and just go, okay, right, just run it end to end with a transformer is the language modeling paradigm now. And what if we're in some, let's maybe, especially Max, some of these kind of maybe medical contexts where we've got very limited data, will diffusion models do well there, or are there kind of tricks or ideas to work with in the low sample regime, or does that really benefit other modeling approaches?
I think like really transfer learning brings you most of the way there. Like I remember when I doing my PhD in transfer learning was like just trying to move your weights over from one CNN to the other. But now like really have these massive models. Like for our work, we can start with a stable diffusion, a VE, just to go to the latency, like to map to the latent space, and it works surprisingly well. Like I would almost go as far as say like this model just learned some general compression scheme. So there we can benefit a lot from the research done on natural images, more than I would have expected.
No, it's really interesting. It's definitely seems that that's the trend. So interesting you're seeing that there too as well. Boris, I know you had a couple of questions for our panelists. Maybe would you like to ask either Sander or Max anything? Great.
Yeah, I'm very interested in metrics of generative models in general and diffusion models especially. And I want to ask both of you, what do you think are the challenges and opportunities for generative model metrics? So, for example, in non-image domains, you might not have an embedder. So we all know that inception is often used for image, for FID scores, say, you can replace it with Dino. But for some domains, you don't have that. And actually training it might lead to very noisy metrics. And for example, going back to what Sander was saying for, say, text generation, do we actually care even about properties like diversity, which we often do care about in the image domain? So your view on metrics.
So yeah, metrics are a problem. Definitely in the perceptual modalities, what we find working on these models sort of at the cutting edge is you just cannot afford not to stare at samples. And at least with images, you can just stare at them. You know, you can put 100 on your screen and stare at them in one go. With audio, you have to listen to them one by one. So that's significant. I think this is why most of these developments happen in the image domain first, right? Because it's just the most responsive of modalities. Like it's the easiest to see the impact of your ideas in. But yeah, it's definitely a problem. I think we have, we use these metrics based on inception networks. If you look at them, I would say at this point they're canaries in the coal mine. Like you look at them to see if your model hasn't blown up. But other than that, we don't trust these metrics, right? Because we're at a level of performance where these metrics kind of break down, and we need to look at sort of the details that maybe these metrics don't accurately capture. I don't have a great answer to what we should be doing there. It would be really, really nice to have some computational metrics that correlate well with human evaluations. Because of course, you know, in industry, we do have access to that. We are able to do human evaluations, but it's not something you can easily do in the loop. Like, it takes too long. You can't send every model you train for evaluation. You have to be picky. So yeah, I think this is potentially a very productive area of research, and maybe one that's also more accessible to academia, because you can do it with pre-trained models, right? You don't necessarily have to go and train your own massive model to construct a good evaluation metric.
Maybe I could just throw that question over to Max as well, especially given the kind of the medical angle there.
I recently became a huge fan of the last paper of Lucas Theist, that asks all these questions that Sander also already now asked. And I love the idea what he proposes there. Basically, he says, like, you have your standard probability measure, right? Like how likely is your sample under some distribution. And then he adds a term that kind of measures the model complexity. And I really love this idea. It's sadly all like, we're not able to compute that, like it goes towards like colomograph complexity and all of these things. But for me, that's such a fresh idea of saying, like, how complex is my model that generates these images, and can I use that? And then he makes really nice connections to compression, like PNG compression, and I think there is like really an interesting opening there. Like, we'll also post that in the chat.
Yeah, I want to add to that. Like, Lucas is kind of a visionary in this area. You know, he had this paper from quite a few years ago, like a note on the evaluation of generative models, that kind of steered the whole space in a different direction and made people realize, oh, maybe we shouldn't be optimizing likelihood when we care about pretty pictures. I'm very honored to have him as a colleague here at Google DeepMind. But yeah, he's his whole sort of back catalog of papers is well worth a read.
I think I'll ask a follow-up question, because I really like the paper, the latest papers of his as well. I think what he didn't really go into much is diversity. So there was, which he doesn't really separate much, and like an FID score or an inception score doesn't really do that either. Some people do that. They say there's realism and there's diversity. What do you think is the relevance of diversity? Because, for example, looking at pictures, you can't actually measure diversity by the naked eye. And maybe sometimes it doesn't matter. Do you have any view on that? Either of you?
Can I ask a clarifying question there? Like, do you, how much control do you want to have over your generative process? Because, like, I wonder, where does the diversity come from? Where do you want it to come from? Do you want to have an unconditional model that nicely maps the whole probability space, or do you rather want to have like very fine control that you then can really nicely, basically, how do I say that? Yeah, generate all these different diverse images.
I think either, right? Like with conditional generation, I think diversity becomes increasingly less important, perhaps, because, like you say, if you want to control a very small part of the space, then it seems reasonable that you don't want diversity by definition, almost. But with unconditional, I guess the diversity is very necessary. So yeah, even defining it is difficult. I agree.
So, and you kind of already made the point that I was going to make, which is that if you have a very strong conditioning signal, then often you can kind of offload diversity to that conditioning signal, right? And this is something that we also saw with OpenAI's DALL-E 3, for example, where they have their language models kind of rewrite the prompt, and you can just rewrite the prompt in 4 different ways and get 4 different images out. It doesn't even matter if the model that's downstream of that, which is a diffusion model, could have completely collapsed for all we know, but it doesn't really matter because we're never sampling from the same prompt twice. Of course, that's a bit of a simplistic representation. There is still a use case for having some diversity there as well, but it does put into context like how much it matters depending on the application area.
And also I want to add, right, like, I guess we're all very happy with classifier free guidance that basically counters the diversity to a certain extent, which I feel like was a big step forward.
Yeah, thank you.
Boris, did you have any more questions that you wanted to ask either Sander or Max?
Yeah, I mean, I guess if I have time, I had a question for Sander. I liked your latest blog about distillation, and I was wondering, so the distillation of diffusion models and making them cheaper to run at inference time. Do you have any insights or opinion on what kind of models we would be? So say you is steps, one diffusion model. It seems quite naive to say, well, we can train a student model that is doing all of that with the same depth, for example, in just a few steps. But I don't see a lot about size, for example, of student models. Do you have any view on this?
Yeah, it's a very good question. So in general, the point I try to make in that blog post is also, if you are distilling your model, you are cutting corners, whether you realize it or not, right? Because you have to be paying some price for reducing the computational cost of generations. And I think people appreciate that, and I think now once you realize that, you can cut corners with intention, right? You can decide, okay, I care less about diversity, so maybe I can mix an adversarial loss into my distillation procedure, or I don't care about fine-grained details as much. You can do something else. Yeah, I'll leave it there.
Okay, thank you. Over to you, Fergus.
Awesome, thanks, Boris. I'm gonna now open it up, I think, to both questions from the audience for our speakers and panelists, because I see a lot both in Slack and in the chat. I think one of the first questions was from John. So I don't know if, John, you want to unmute yourself and then briefly ask your question and who it's to, and then we'll try and get through as many as we can in the time remaining. If not, maybe I'll read out John's question. I think it's to our first presenter, Nico. Is diffusion in the frequency domain computationally more efficient? And then I think, Nico, maybe you want to take Amy's question as well about the input to the SDE and the form it takes.
Yeah, sure. So regarding the computational cost, so the DFT maps the time series to the same dimensionality. So there's not a big difference in computational efficiency. It's basically the same. And we also timed the trainings of the models, and we saw that empirically it's kind of similar. So not a big difference between the two. The second question is, what is the input X in the SE? Yeah, so in this work we worked on time series which can have multiple dimensions, and what we did is that the depth is the number of time steps as is written in the questions, and of course you have the number of channels, which is the number of dimensions in the time series.
Awesome, thanks, Nico.
If it's okay, I have one more thing to say in response to Boris, because I realized I only kind of answered half of his question, and he asked also about distilling diffusion models not just into fewer steps, but maybe into smaller models, right? And I agree, it's very interesting that there's very little work on that apparently, because it's actually a very nice setting for this kind of distillation. And the way to see that is if you train a diffusion model from scratch, you wanted to learn to predict expectations, right? You wanted to learn to predict the expectation of the clean input given the current noisy input. What is the average of all possible clean inputs that could have given rise to this particular noisy input? But to train that model, we're actually supervising it with specific examples, right? We don't supervise it with the expectation. We supervise it with specific samples from the data set. And so that is inherently a very high variance loss function. But when you go over to the distillation setting, now you have a teacher that is already giving you an estimate of the expectation, and you're using that for supervision. So one thing that you will find in this setting is that the distillation loss converges way faster than the standard training loss. It has much lower variance. And somehow we haven't really leaned into that. I haven't seen many papers sort of trying to take advantage of that. Thanks.
No, thank you, Sander, so much for adding that. I think it's definitely a really interesting point, especially when we think about kind of inference costs and inference times as well. That's super interesting. I think there's a question from Marty Glassman. I don't know if you want to ask a question. I think maybe it's towards Sander, but I don't know if you want to ask it to anybody else. Do you want to, if you're still here, do you want to unmute yourself and ask? Let me, why don't I read it out then? In working with music or speech, is there any thought of incorporating explicit models of processing in the human auditory processing, such as forward masking in time?
Don't know about forward masking in time specifically, but I do think that there is interest in bringing in signal processing knowledge. Specifically, I thought a really interesting example was Diffusion. Don't know if you've seen that. It was quite a while ago now, but it was basically a few guys who took stable diffusion, I think it was SDXL or maybe the first one, and decided to fine-tune it on spectrograms. They basically just converted a bunch of music excerpts to images of spectrograms and then fine-tuned stable diffusion on this. And surprisingly, this worked remarkably well. Like, this was like a fairly impressive, in my opinion, music generation model. And when that first happened, it really frustrated me because it makes no sense at all, right? Like, treating a spectrogram as an image is weird because spectrograms don't have the same statistical characteristics as images. You know, in images, you have this kind of translation invariance concept, which actually doesn't apply in the frequency axis of a spectrogram. But the reality is that it worked quite well. And this is also linked to something that Max said earlier. They used an image model and then fine-tuned it on spectrograms and somehow benefited from that image pre-training in a very different domain, right? So there's, as Max said, there's kind of like almost something fundamental in natural signals that these models are learning that is valid even across modalities. So yeah, I think there's definitely room for bringing in what we know about sound to improve these models.
Thank you so much.
Can I also add something to that?
Yeah,
like,
please,
because
please
in the beginning we had like this whole idea of like we can use the diffusion models for so many modalities, and of course, what I always then wonder is what do we lose by making that work, right? I feel like there is a tendency, what Sander just mentioned, like, oh, if I can turn music into a spectrogram, then I can use all the Hugging Face code for images. And I feel like there's also a tendency of people doing that. And then I have a lot of questions about phase that's usually getting thrown away, like part of the musical signal getting thrown away. And then, yeah, I feel like there's a bit of a trade-off always of like, yeah, we can map a lot of modalities, but maybe you also force it a bit. So there, I just wanted to add that.
No, thank you. I see we only have a few minutes left, so I think Sander already threw out a couple of challenges to all of us here, which is, if you're interested, I guess, on the distilling models down and also on model evaluation. Are there any other challenges or opportunities either of you would like to share with the audience or throw out, or just any closing comments in general that Sander or Max you would like to make before we wrap up for today?
I think another area where new research is welcome is the kind of equivalent of RLHF for this class of models. Like, we're really trying to figure out how to align large language models. There's quite a few papers now trying to do the same with diffusion models of various modalities, but I think it's still less mature at this point. It's less clear what the method is that we should be using. Yeah, I think that's the big one, apart from the ones that I'd already mentioned before.
Awesome, thank you. Max, is there anything you'd like to add?
No, I think that covers it pretty well.
Awesome, thank you both. I'd really like to thank you, Sander, and you, Max, for joining us today for that discussion. I think there's a lot of things I want to think more about as I think more about diffusion models, and I hope our audience enjoyed it just as much as I did. just before we close, I would like to just mention that the Schaar Lab is running a summer school this summer on AI and machine learning, covering a wide variety of topics taking place in September. So if you're interested in joining, you can find more information using the QR code on the slide or by going to the lab's website. And finally, this is our last session before the summer break, and then Inspirational Exchange will reduce back in a few months' time. So stay tuned for more info there. And with that, I'd just like to say again, just one more massive thank you to our two presenters from the group, Nico and Yanming, and our two guests from industry, Sander and Max, for joining us today for what I think was a really awesome session to wrap us off before summer. So thank you very much, and hope to see everybody in a few months' time.